Let me highlight no one is on. You're here to join. Yes. We have 88 already.
Yes.
Okay.
Hmm?
Okay. Thank you, ma'am.
Yes.
Yes. Good afternoon, everyone. Good day, everyone. Good day, everyone. So I welcome you to Physics 102 class. Today we'll be looking at Maxwell's equation. So in this topic, we'll be looking at the four basic equations of electromagnetism. So we'll be looking at magnet and electron and the three basic magnetic materials. So if you recall from your previous classes, so you were given the Gauss law for magnetic, for electric field. So the Gauss law for electric field is giving us this equation. That is the electric field is charged enclosed by that field. And this equation, when it is applied to magnetic field, because in magnetic field, there is no magnetic charge. So there's no magnetic charge, unlike electric charge. You know, we have electric charge, it may be positive, it may be negative. Positive, that's the source, and negative, the sink. But in magnetic field, there's no magnetic charge. So, and what does this mean? It means that magnetic monopole magnetic monopoles do not exist. So no matter how small a magnet is, it will have the dipole, that is the north and the south poles. So magnetic monopoles do not exist. Please take note. So because of this, that is the charge enclosed by the magnetic field, will be zero. It will be zero. So, therefore, the Gauss law for magnetic field is given as this equation. That's phi b, that's integral of the magnetic field dot dA. Induced magnetic field In your previous classes, you were made to understand that changing magnetic flux induces an electric field. That is Faraday laws of induction. That is, changing magnetic field flux induces an electric field. And this law was modified. This law was modified by Maxwell. It was modified by Maxwell. And the modification is a changing electric flux. You know, in Faraday, we have changing magnetic flux. So in this one, it is changing electric flux induces a magnetic field. Changing magnetic flux, that is d phi e dt, induces the magnetic field, that's B. So as you can see in this equation. So this equation is the modification of the Faraday's law of induction, and it is known as the Maxwell's law. So this is the Maxwell's law of induction. Now, it relates the magnetic field induced along a closed loop to the changing electric flux through the loop. Okay? And this was demonstrated by these experiments. The changing of the electric field between the plates creates a magnetic field, that is charging a capacitor. Charging a capacitor. Now, if you recall also from your previous classes, you were given the Ampere's law. The Ampere's law to be the integral of BDS is equal to mu naught I enclosed, that is the current enclosed. Okay, the Ampere's law gives the magnetic field generated by current. You know, when current passes through a wire, it generates magnetic field in the loop. So if you now compare this Maxwell equation, okay, and we combine it with this Maxwell equation, the result will give us this equation. If you combine the Ampere's law and the Maxwell's law of induction, where we combined it together, it will give us this equation. And this equation is known as Ampere's Maxwell law. So this is Ampere-Maxwell law. And what can we deduce from this law? If there is a current but no change in electric flux, there is a current but there is no change in electric flux, this component of the equation will be zero. This component of the equation will be zero. And this equation, this Ampere's Maxwell equation, will then be reduced to Ampere's equation, that is Ampere's law. Also, if there is a change in electric flux, but there is no current, this aspect of the equation will be zero, and this equation will be reduced to Maxwell's equation. To reduce to Maxwell's equation. Now, from that equation, that's Ampere's-Maxwell equation here, this component, we can see that it must have the dimension of a current. That is, so that we can compare with this. You know, this one has a component of, we have the current here. So this one also, okay, we can replace it with what we call the displacement current, I sub d. That is, this component, if you want to compare this, we want to compare with this. So this must have the dimension of a current, and it is called the displacement current. It is called the displacement current, I sub d. So if you now replace this, if you replace it in the Ampere-Maxwell's law, so that equation will be reduced to this, where I sub d is known as the displacement current and is given as epsilon sub naught d phi e dt, d phi dt, and that is known as the displacement current. And this displacement current, we can relate it with displacement current density. We can relate this with the displacement current density, that is current per unit area. Current displacement current density. This is current per unit area. Current per unit area. Now, we know that changing electric flux will induce a magnetic field. Now, what we now need to do now is to find the magnitude and the direction of this field. We want to find the magnitude and the direction of this field. The direction of the field is given by, if you want to know the direction of the field, we're going to apply the right-hand rule. So we can apply the right-hand rule to obtain the direction, to note. So the right-hand rule, when it is applied, it will give us the direction. But the magnitude of this field. Now, we need to understand something. If the field, if R is less than this, it means the point is inside the capacitor. And if it is less, if it is greater rather, it means the point is outside. So that's why we have two different equations. So the first one is the point is inside. So the magnitude of the magnetic field at a point inside the capacitor at radius r from the center is given at this equation. Please take note of it. The magnitude of this induced magnetic field the magnitude of this induced field, if the point is inside the capacitor, is given as this. And if the point is outside, is given as this. Now, how will you now differentiate or how will you know whether the point is inside or outside? At Ramon Nafis. So thank you for your observation. Thank you for your observation. Don't worry, I'm going to release your test result very soon. Then some of you will now realize that there's one verse of the Bible that will apply to some of you. It said, he who thinks he stands, take heed lest he falls. Because some of you, maybe you think on your own, if you have the material, you can develop yourself, you can face the exam and pass. And some of you, what you normally do is you can't reason on your own. You can't reason. Whatever you see someone else doing, you tend to copy them, and it's going to affect some of you, because out of about 5,000 candidates, so we have less than 100 attending the class. It is somehow appalling, so pathetic. Well, don't worry, I'm going to release your result very soon. I think being you have access to your 101s, you will have, I believe by now, some of you will have at least adjusted. You'll have adjusted. But it's because I don't know. But don't worry, your test result, I'm going to release that result. Out of 5,000, less than 2,000 scored above 10. So which means about 3,000 scored below 10, failed. We even have at least numerous people scoring like 1, 0, 1, 2, 1, 2, 3 over 20. Well, don't worry. Okay, you can hit your cake and have it. A word is enough. A word is enough. It's network problem. MFS service to working well. Okay, maybe you should try and change your location, please. Yes. Now we're talking about the magnitude of this induced magnetic field. That how can we obtain it? How can we obtain the magnitude? And how can we know the direction? Don't forget that the field, the magnetic field, is a vector quantity. So direction and the direction is very, very important. So if you want to deduce the direction, so what we're going to do is to apply the right hand rule. The right hand rule. When you apply it, this will give you the direction. Okay, and the magnitude. The magnitude, you have two different equations that you can use to obtain the magnitude. But you have to, okay, before you apply any of the equations, so you have to know whether the point is inside the capacitor or is outside the capacitor. If it is inside the capacitor, the radius will be smaller, that is less, to be less. And if it will be less than the radius of the plate. Okay, that's the center from the point from the center of the plate, okay, which is R. It will be less than the radius of the plate if it is inside. But if it is outside, the point will be greater than the radius of the plate, because if it is outside, it will exceed to beyond to be greater than the radius of the plate. So please take note of this. This is why I brought this thing. Okay, don't worry, we're going to do this one later. Okay, let's continue with the class. Yes. Now, so we started with this equation. You're all familiar with this. You've done this one before. Okay, that's this Gauss law for electric field. Okay, that's from the first lecturer rather. This one from the first lecturer. That's Gauss law for electric field. And the Faraday's law of induction from the second lecturer. Okay, so this is the third one. This is the third one. That's Gauss law for magnetic field. And finally, you have this, which is the fourth one, which is Ampere-Maxwell's law. So these are the four basic equations, okay, of electromagnetic phenomena. So these equations, these are called Maxwell's equation. So these four equations are called Maxwell's equations. So the first one, and the physical interpretation. So you have Gauss law for electricity. So so what's the physical interpretation? It relates net electric flux to net enclosed electric charge. So the second law, that's Gauss law for magnetism. So what does this inform? So this one, it tells us that magnetic monopoles do not exist. Magnetic monopoles do not exist. Okay, so it relates net magnetic flux to net enclosed magnetic. And this is the Faraday law of induction. So it relates induced electric field to changing magnetic flux. And the last one, Ampere-Maxwell's law. So this relates induced magnetic field to changing electric flux and to current. So these four equations explain a diverse range of phenomena, from where a compass needle points, not to why a car starts when you turn on the ignition key. So these are the basis for the functioning of such electromagnetic devices as electric motors, television transmitters and receivers, like the antenna, so telephones, scanners, radar, and microwave ovens. Now we want to look at magnetism and electron. So these aspects will enlighten us, need to make us to know that electrons can also behave. They can behave as a magnet, as a tiny magnet. So electron behaves like a magnet. Okay. There's some natural, electron has some natural characteristics, like the mass, the charge, the electric charge. It also has another characteristics, that's inbuilt characteristics, okay, known as spin angular momentum. Spin angular momentum, denoted as S. Spin angular momentum, denoted as S, and is a vector quantity. Is a vector quantity. And this spin angular momentum is associated with spin magnetic dipole moment. Spin magnetic dipole moment. So these are natural characteristics of an electron. Okay, and this spin angular momentum and spin magnetic dipole moment are related by this equation. They are related by this equation, where E is the elementary charge and the value is 1.60 times 10 raised to minus 19 coulomb. M is the mass of the electron. M is the mass of the electron, and whose magnitude is 9.11 times 10 raised to minus 31 kilograms. And this minus sign, it means that the spin angular momentum and spin magnetic dipoles are oppositely directed. That is, if one points upward, the other one points downward. Okay? Now, before we continue, let me give the first attendance. Before we continue with the class, let me give the first attendance code. First attendance code. NLRP X. So that's the first attendance code. NLRPX. Yes. So said electron has some natural characteristics. So we have the electric charge, the mass, but also have spin angular momentum. You know, as this electron spins, okay, up and down. So it has, due to this, it has angular momentum. And this angular momentum is a vector quantity. And associated with this, and associated with this angular momentum is this spin magnetic dipole moment. And the two are related by this equation, okay, where E is the elementary charge, M is the mass, moon S is the spin magnetic dipole moment, S is the spin angular moment. Now, the component of this can only be measured along the Z axis. And along that axis, the component of this, the component of the spin angular momentum has this value. That is, xz is equal to ms h over 2 pi. Sz is equal to ms h over 2 pi. That is the value of the spin angular momentum along the Z axis. So similarly, the spin, this one, will now be, you know, when you combine this and this together, okay, along this spin angular momentum along the Z axis. So just multiply this with this. So we have something like this. So this E multiply with H, okay, and you know, the ms here, if you make ms the subject of the equation from here, let me just quickly do that. So you have ms is equal to h over 2 pi okay, no, it's not it. Now just replace this with this in this equation. If you replace the spin angular momentum here, replace with this value in this equation. So we have h, this will multiply this, and this will now have 4 pi m. So, and is equal to plus or minus is equal to plus or minus this. Okay, plus or minus mu B. So where this is ball magneton and ball magneton is this. E is the elementary charge. So just put the value of this H, 4, pi, and M. By the time you insert these values and substitute everything and calculate using your calculator, you are going to have this constant. And this constant is known as the ball magneton. Now, the energy, we need to find the energy associated with the orientation of the electrons spin. The energy associated with the orientation of the electron spin. Now, the electron spin, it's the value, this ms. ms is equal to plus or minus half. Please note, ms is the spin, okay? ms is the magnetic spin, and the value is plus or minus half. Now, it is plus half when its direction, when it points upward, and it is minus half when it points downward. So if you substitute this half, substitute half for ms here, okay, so sz will be this over plus or minus 4 pi. 4 pi, okay, 4 pi, and put the value here so you get this, okay. Now, the energy, you want to look at the energy associated with this, the orientation of the electron spin. So when an electron spin is placed in an external magnetic field, so an energy you can be associated with the orientation of the electron spin magnetic dipole moment. So, and the energy is given as this equation. So you have U is equal to minus mu S dot B. So this is the external magnetic field, and this is the electron electron spin magnetic dipole moment. And this is a dot product. Dot product, the dot product of two vectors will give us a scalar. The dot product of two vectors will give us a scalar, and this will result to this. So if you want to find the energy associated with the electron, the orientation of the electron spin, so this is the formula that we use, okay? And this is always along the z direction because other component cannot be measured. So we can only measure, okay, the one that is along the components along the z axis. Also, we know that electron, it revolves around the shell of an atom, okay? You have the neutron and the proton at the center, and you have the electron revolving around the shell. So this, as electron is moving, is revolving around, okay, it exhibits what we call orbital angular momentum. Angular orbital momentum, denoted as this L orbital, that's suborbital. And associated with this L orbital is an orbital magnetic dipole moment. And this orbital angular momentum and associated orbital magnetic dipole moment are related by this equation. And the minus sign the minus sign means that the L orbital and the angular momentum and the magnetic dipole moment are in opposite direction. So when one points upward, the other one points downward. Okay, so the minus sign means that the dipole moment and angular orbital, they have opposite directions. So the orbital angular momentum is quantized. Okay, that is, can only take some specific value, and the values are this. So ML is equal to 0, plus or minus 1, plus or minus 2, so on and so forth. So we have L orbital is equal to ML over this. So when ML is 0, L orbital will be 0. Okay, so when ML is 1, so L orbital will be H over 2 pi. When it is minus 1, it will be minus. So if now substitute this one, this for L orbital here, put it here. When you put it here, we can now rewrite the magnetic dipole moment. We can rewrite it in this form. So this will be E times this, and 2 times 2 will give you 4 pi, and this is ML. Don't forget that from the previous slide, EH over 4 pi M is equal to mu B. That is the magnetic, the Bohr magneton. So we can replace, if you replace this one with it, so that's, we have something like this. Okay, and the energy associated with the orientation of the orbital, that's orbital magnetic dipole, is given as this. Okay, that's the dot product. Dot product between two vectors will give us scalar, give us a scalar. Okay, so give us a scalar, and that is why we have something like this. So we want to look at magnetism in materials. Magnetism in materials. When a material is placed in an external magnetic field, it responds differently depending on the arrangement of its electron. So based on this response, materials are classified into 3 main groups. So you have diamagnetic materials, we have paramagnetic materials, and we have ferromagnetic materials. So the difference between them lies in how strongly they are attracted, or they are attracted to, or they are repelled by a magnetic field. There are some that are weakly attracted, there are some that are weakly repelled, and there are some that are strongly attracted. Okay, so let's start with the first one, which is diamagnetic material. So how will you know that a material is diamagnetic? Okay, now the material is diamagnetic if when you bring the material close to an external magnetic field and it repelled, then the material is diamagnetic. Okay, so diamagnetism is the property of materials that causes them to be weakly repelled by an external magnetic field. So before we continue with this slide, so let me give the second attendance code. So you have D845Y. D845Y. That's the second attendance code. It's not T, it's D from dial. D for dial. D845Y. Y for yes. Abdulmuis, please take note, okay? D8, D8, that's Dayo 845 Y, okay? Yes. Now let's continue. So every material exhibits that magnetism to some extent, but in most material, it is marked by stronger magnetic effect. So the electron, so we look at the arrangement of electrons in that magnetic materials. The electrons move around the nucleus. So we know that the electron move around it, revolve around the nucleus. So when an external magnetic field is applied, these electron motions change slightly. Okay, change slightly. So according to Lenz's law, so the induced magnetic field opposes the applied field. So it changes, the direction changes, okay? And from Lenz's law, so the induced magnetic field, it opposes the applied field. So as a result, the material develop a magnetic moment opposite to the applied field. And what happened? The material is repelled. Okay, so that's that about that magnetism. So in the magnetic materials, all electrons are paired. That is, they are paired in opposite direction, like this. Electrons are paired. So each electron has an opposite spin partner. So if the other one spins up, the partner spins down. So when the first one spins up, the partner spins down. So the magnetic effects cancel each other, that is, cancel out. Okay, so therefore the atom has net magnetic moment. Okay, has net magnetic moment. Paramagnetism. The paramagnetism is different from that one. This is different from that magnetism. So a paramagnetic material placed in an external magnetic field, B, it develops a magnetic dipole moment. Okay, even the diamagnetic material, we also develop a magnetic dipole moment, but it's just that in opposite direction to the applied field. Okay, in opposite direction to the applied field. But paramagnetic material will develop a magnetic dipole in the direction of the applied field, in the direction, same direction. So if the field is non-uniform, the paramagnetic material is attracted towards the region of greater magnetic field from a region of lesser field. But the moment the external magnetic field is removed, withdrawn, the paramagnetic material will lose its magnetism or magnetization. To lose it, it cannot retain it. Okay, so the moment the external magnetic field is removed, the paramagnetic material will lose its magnetism. So let's look at ferromagnetism. So ferromagnetism is the property of certain material that causes them to be strongly attracted by magnetic field and allows them to retain magnetism even after the external field is removed. So that's the difference between ferro and para. For paramagnetic material, okay, so it is attracted by the magnetic field, but the moment the external field is removed, it will lose its magnetism. It cannot retain it. But ferromagnetism will retain its magnetism even after the external magnetic field, okay, has been removed. So when it is removed, it will still retain it. So inside ferromagnetic materials, there are tiny regions called magnetic domain. So each domain acts like a tiny magnet. So without an external magnetic field, the domain points in different directions. Okay, so their effect cancel out, the overall effect cancel out. Okay, so but when a magnetic field is applied, this domain now rotates and aligned in the same direction. They are aligned in the same direction. Okay, and this produces a very strong magnetic effect. So even after removing the external field, many domains remain aligned. Okay, so we can look at this table to we compare the three types of the magnetic material. So you have the property, we have diamagnetic, we have paramagnetic, and ferromagnetic material. So response to magnet, the diamagnetic, they respond very weakly, weakly repelled, and paramagnetic, weakly attracted, but ferromagnetic, strongly attracted. So unpaired electrons. So that magnetic has no unpaired electron. So there's some unpaired electron being present in paramagnetic and ferromagnetic material. Net magnetic moment. The net magnetic moment is zero in diamagnetic because the spin, that paired spin, they spin in opposite direction. Okay, and the effect cancel out. Okay, so the net magnetic moment is zero for that magnetic. So and it's also zero for paramagnetic, and net magnetic moment is zero for that magnetic, very small for paramagnetic, and large for ferromagnetic material. Now retains magnetism. That magnetic material do not retain magnetism. Paramagnetic do not retain magnetism, but ferromagnetic materials do retain magnetism. So magnetic susceptibility, so it is negative in diamagnetic and small positive in paramagnetic and very large positive in ferromagnetic. And the strength, so very weak, moderate, and very strong. Very strong. Google form isn't accepting response. There's nothing we can do. Okay. So that's that about that aspect. Let's quickly look at this question. I have some practice questions, okay, here. So let's look at the first one together, and on your own, you can solve the remaining questions, okay? Now, I forgot to insert plain. So let's look at this, the first question. So we're going to look at the first question. So I'm going to dictate the question. So as a parallel plate capacitor with circular plate 20 centimeter in diameter is being charged, the current density of the displacement current in the region between the plate is uniform and has a magnitude of 20 ampere per square meter. Calculate the magnitude B of the magnetic field at a distance R equals 50 millimeter from the axis of symmetry of this region. And B calculates the E dt in this region. Calculates the E dt in this region. Now, before we continue, let me give the last code, okay? Attendance code. So just take it. So the last one, the last code, PZFDF. So that's the last one. That's the last one. So let's look at the question. Say as a parallel, PZFDF. That's the last code. The last. So as a parallel plate, capacitor with circular plate, 20 centimeter in diameter, is being charged, the current density of the displacement current in the region between the plates is uniform and has a magnitude of 20 amperes per square meter. Calculate the magnitude B of the magnetic field at a distance R equals 50 millimeter from the axis of symmetry of this region. Okay. So we'll look at the given parameters. So we are given the radius of the plate, which is R, is equal to 20 centimeter. I mean the diameter of the plate is 20 centimeter. So radius will be diameter over 2 equals 10 centimeter, which is 0.1 meter. 0.1 meter. So we're given the magnitude of the current, that's current density. Current density. So we're given current density, J sub D, to be 20 ampere per square meter. So we have to relate the current density with the displacement current. So what's the relationship between current density and the displacement current? So we have current density is equal to the displacement current divided by the area. That's the current per unit area. Okay, so this is if you make the displacement current the subject of the equation, we have this. That's the current density.